Section: Introduction. In this section, we discuss representation learning, which is crucial in machine learning for extracting and encoding valuable information from data. Supervised learning, especially classification tasks that minimize cross-entropy, has become the leading approach in deep learning. Despite its straightforward nature, this method has led to fascinating phenomena, such as neural analogy making, the linear representation hypothesis, and the success of transfer learning. These suggest that deep learning models can encode features in a way that allows for linear decoding. However, a complete theory explaining why these properties arise in deep learning models is still lacking. To fill this gap, we build on the theory of independent component analysis, ICA, which examines how latent variables in probabilistic models can be uniquely identified. Recent advancements have extended ICA to nonlinear models, providing a theoretical basis for recovering latent variables across various machine learning tasks. Most of this work has focused on semi-supervised learning, where neural networks learn from unlabeled data by solving a surrogate classification task. We aim to explore whether similar identifiability guarantees apply to cross-entropy-based supervised learning, where labels are provided. We begin by noting that nonlinear ICA has shown identifiability guarantees in contrastive learning, where models recover latent variables through linear transformations. We extend this concept to a simple form of semi-supervised learning using the diet method, which simplifies the auxiliary task into an instance discrimination framework. We model the data generation process in a cluster-centric manner and demonstrate that the representations learned by diet are linearly related to the true representations. From this foundation, we extend our theoretical framework to standard supervised learning, showing that models can recover true latent variables up to a linear transformation in typical classification tasks using cross-entropy loss. This helps explain why deep learning, particularly in supervised classification, is effective in learning interpretable and transferable representations, providing a unified framework for understanding phenomena like linear representations and neural analogy making. Our contributions include proposing a cluster-centric data generation process to establish the linear identifiability of the instance discrimination objective, extending identifiability guarantees to standard cross-entropy-based supervised classification, and connecting our results to auxiliary variable nonlinear ICA and semi-supervised learning. We validate our findings through synthetic experiments and real-world data, demonstrating that cross-entropy loss can lead to linear identifiability of features, regardless of label meaningfulness. We also highlight the recent interest in the linear representation hypothesis, which suggests that certain directions in neural activation correspond to interpretable features. For instance, in neural analogy making, specific directions in word embeddings can represent concepts like gender. Various datasets have been created to assess this phenomenon, and theoretical frameworks have been proposed to clarify the linear representation hypothesis. However, these frameworks do not connect to cross-entropy-based classification, which is a gap we aim to address. Section Summary. In this section, we explore the significance of representation learning in deep learning, particularly focusing on how cross-entropy-based supervised learning can recover interpretable and transferable representations. We build on the theory of nonlinear independent component analysis, ICA, to establish that models can achieve linear identifiability of latent variables, thereby explaining the effectiveness of supervised classification in learning meaningful features. Section: Identifiable Weakly, Self-Supervised Learning and ICA. In this section, we explore identifiable weakly and self-supervised learning, along with independent component analysis, ICA. ICA theory examines the conditions under which hidden variables in probabilistic models can be uniquely identified. Identifiability means that the representation we learn at the best point in our training relates to the true representation through simple transformations, like rearrangements or invertible changes. This differs from studies that compare two learned representations. Recently, ICA has been adapted for nonlinear models, which helps in recovering hidden variables across various learning tasks, particularly in self-supervised learning. Our main theoretical contribution begins with our motivation to understand self-supervised learning using the simplified diet algorithm. We propose a cluster-centric deep generative process that models semantic classes. We present our main findings and discuss the intuition behind diet's identifiability. We also examine how diet fits into the broader literature on identifiable self-supervised learning and auxiliary variable ICA methods. This leads us to a significant result for supervised classification, demonstrating its identifiability under the diet framework. Despite advancements in theory, we still struggle to understand why self-supervised learning methods perform well in practice. We identified two gaps. First, practitioners often discard the last layers of the encoder for better performance, which isn't reflected in identifiability guarantees. Second, the data is likely clustered, contrary to the assumption of uniform distribution. While auxiliary variable nonlinear ICA methods share similar terminology, their relationship to self-supervised learning remains unclear. Notably, identifiability proofs for nonlinear ICA separate the encoder from the regression function, showing that latent variables are identifiable after the encoder but before the regression. This aligns with the practice of discarding the projector in self-supervised learning, even though identifiability results do not support this. Our goal is to extend identifiability guarantees to more realistic self-supervised classification scenarios and apply these insights to enhance our understanding of supervised learning. We aim to deepen our theoretical understanding of self-supervised learning using the diet framework, which offers strong and realistic results due to its similarities to other methods. Diet employs a separate encoder and classification head, solving an auxiliary classification task, and its loss correlates with downstream performance, which is a valuable insight. In our setup, diet addresses an instance classification problem where each sample in the training dataset has a unique label. Augmentations do not change this label. We utilize a composite model where the backbone generates representations, and a linear classification head maps these to a logit vector matching the dataset size. The logit corresponding to a specific label computes similarity scores with the embeddings. Diet trains this model to predict the correct instance label using multinomial regression, leveraging cross-entropy loss with instance labels to connect instance discrimination to supervised classification. Section Summary. In this section, we explore the identifiability of weakly and self-supervised learning, SSL, through the diet algorithm, proposing a cluster-centric model that captures semantic classes and demonstrates how diet structure aligns with supervised classification. We aim to bridge the gap between theoretical guarantees and practical applications by proving the identifiability of representations used in downstream tasks and highlighting the significance of the encoder's role in SSL. Section. The proposed cluster-centric less than DGP greater than. In this section, we propose a cluster-centric data generation process, DGP, to demonstrate the identifiability of latent variables. We define a latent variable model, LVM, for our DGP, using cluster vectors to represent semantic classes, similar to proxy-based metric learning. We model class samples with a von Mises-Fisher, VMF, distribution, which is like a multivariate normal distribution but constrained to the unit hypersphere, centered around the class's cluster vector. This approach allows us to jointly model the selection and augmentation of samples within a class, referred to as intra-class variances. Unlike traditional self-supervised learning, SSL, methods like InfoNCE, our model separates the global and local structures in the latent space. The cluster vectors capture the global structure, while the cluster-centric conditional captures the local structure, ensuring that data augmentations do not alter the sample's semantic class. We clarify that this does not imply that every sample pair can transform into each other through augmentations with high probability. Instead, we assume that all semantic concepts correspond to a continuous latent variable, leading to a connected latent manifold. We outline our assumptions, which include having a finite set of semantic classes represented by unit norm cluster vectors, that each instance label belongs to one class, and that the latent variable for a sample is drawn from a VMF distribution around the corresponding cluster vector. We also state that each sample is generated by passing its latent variable through an injective generator function. Our main result shows that diet can identify both latent variables and cluster vectors across different types of embeddings. Intuitively, diet assigns a unique label and weight vector to each training sample. The cross-entropy objective is optimized when the neural network can differentiate between samples, ensuring that the learned representation captures enough information to distinguish samples, even within the same class. However, the weight vectors cannot be sensitive to intra-class variance, leading them to align with the cluster vectors. This means that while cluster vectors capture some statistics, feature recovery is more detailed than just identifying clusters. The interaction between these elements is governed by the cross-entropy loss, which is minimized when the representation closely matches its assigned weight vector. In relating our cluster-centric DGP to supervised classification, we note that supervised learning can be seen as a specific case of self-supervised approaches. The sample index, which targets the cross-entropy loss, can be defined in various ways, including those used in supervised classification. This insight highlights the success of supervised cross-entropy-based classification, as it effectively performs nonlinear independent component analysis, ICA. In the context of diet, the cross-entropy objective encourages learned representations to align with the cluster vectors for each class. The identifiability of latent variables is supported by the cluster structure reflecting the underlying data distribution modeled as a VMF distribution. This results in a representation that captures the latent structure up to an orthogonal transformation. Thus, supervised learning can be viewed as a special case of instance discrimination, where instance labels are replaced with class labels, leading to a theoretical understanding of the success of supervised classification in learning linearly decodable representations. Section Summary. In this section, we propose a cluster-centric approach to identify latent variables in a data generation process, DGP, by modeling semantic classes with cluster vectors and using a von Mises-Fisher distribution to capture intra-class variances. We demonstrate that our method aligns with supervised classification, showing that the cross-entropy objective encourages learned representations to reflect the underlying data distribution, thus explaining the effectiveness of supervised learning in producing linearly decodable representations. Section: The genealogy of identifiable classification with cross-entropy. In this section, we explore the relationship between identifiable classification and cross-entropy. Our main findings indicate that by optimizing the cross-entropy objective, we can effectively solve various classification tasks and identify the true representation of the data, allowing for a linear transformation. We demonstrate that solving a classification task based on cross-entropy is crucial for achieving this identification. We present a unified view of different classification methods, including weakly supervised and supervised approaches, which we refer to as a genealogy, highlighting their interconnectedness. Starting with the most general framework, we consider auxiliary variable nonlinear independent component analysis, ICA. This framework operates with independent latent variables in a space defined by auxiliary information. It aims to classify different values by distinguishing between them based on an auxiliary variable. At the optimal point of the cross-entropy loss, this framework allows us to identify latent variables before the classifier, up to invertible transformations. When we focus on a specific case where the auxiliary variable is a scalar, we derive a more specialized method. If the latent variables follow a simple exponential family distribution, we achieve identifiability only up to a linear transformation. Next, we apply our cluster-centric data generation process to a special latent distribution, which gives us identifiability guarantees for our diet method. Here, the auxiliary variable is again a scalar, but it represents the sample index. Our main result also applies to unit normalized representations, commonly used in identifiable self-supervised learning methods like InfoNCE. This shows that our findings are broader than just nonlinear ICA, as they confirm identifiability for latent variables used after training. When we consider supervised classification, where labels are semantic class labels rather than arbitrary indices, our identifiability result still holds. In our empirical results, We validate our theoretical claims in a synthetic setting by generating data samples based on our assumptions. We describe our findings on the dislib disentanglement benchmark and present experiments on ImageNet-X. For our setup, we generate latent samples of a specific dimensionality from a conditional distribution, using an invertible multilayer perceptron to map these latent variables to data samples. We train a classification head and an encoder using the diet objective. We verify our theoretical claims by measuring the predictability of the ground truth from our representations using the R-squared score on a held-out dataset. We also assess identifiability through linear transformations, checking the convergence of singular values and evaluating the performance of linear predictors. Section Summary. In this section, we demonstrate that optimizing the cross-entropy objective for classification tasks can effectively invert the data-generating process, DGP, and achieve linear identifiability of latent representations. We provide a unified framework linking various classification methods, including weakly supervised and supervised approaches, and empirically validate our theoretical claims through experiments on synthetic data and benchmarks like ImageNet-X. Section. Results for diet. In this section, we present the results for diet. In our table of experimental results, we show the R-squared scores for recovering cluster vectors and ground truth latent variables. For diet's PID task, we also look at cases with row-normalized data. We find scores close to 346, even with many clusters and samples. However, high latent dimensionality affects the recovery of ground truth latent variables, which is a common issue in semi-supervised learning. When we have a higher concentration of samples and fewer clusters, the R-squared score decreases, likely due to excessive overlap in augmentations. With a low number of clusters and a fixed number of training samples, we see an increase in sample concentration around centroids, which is known to be suboptimal and can reduce performance. Our findings indicate that even with model misspecification, identifiability remains intact. For unit-normalized rows, the mean absolute error is lower, confirming the orthogonality of the mapping. We also include an additional study on sample concentration across the unit hypersphere. Next, we discuss results for supervised classification. In our table of simulation results, where we used semantic class labels instead of sample indices, we only report the R-squared score for recovering ground truth latent variables. Interestingly, we observe higher R-squared scores from representations learned with class labels in almost all settings. This suggests that even a simpler classification task can effectively learn identifiable representations of the underlying latent variables. We then evaluate our methods on the dislib disentanglement benchmark, which provides a controlled environment for testing disentanglement and latent variable recovery. This benchmark includes various vision datasets. We train both a 3-layer MLP and a CNN, both with 399 latent dimensions. We focus on latent variables with Euclidean topology, as non-Euclidean variables can be challenging to learn. We assess the recovery of latent variables by calculating the Pearson correlation between ground truth and predicted factors. Our models trained with cross-entropy successfully recover latent variables like object position, scale, and orientation with high accuracy. The Pearson correlation is generally highest when predicting latent variables from the CNN's representation. In some cases, such as position in DS-sprites, we achieve high accuracy even on the input data. However, we find that the nonlinear function estimated by the model is essential for correctly identifying the latent variables. Finally, we test the generalizability of our theoretical insights on real-world data using ImageNet-X, where latent variables are defined by human annotators. We evaluate how well linear decoders can predict latent variables from pre-trained model representations using two architectures. We report accuracy, correlation, and F1 score, plotting these metrics against a random baseline. Our results show that even with complex, high-dimensional data, representations learned through supervised learning allow for linear decoding of latent variables above chance performance. However, we note that these latent variables may not represent the true underlying variables of the data generation process. One limitation of our work is our focus on synthetic and controlled datasets. While results on ImageNet-X are promising, further experiments on other large-scale datasets would strengthen our findings, though this requires datasets with complete latent variable annotations. Our cluster-centric modeling captures the inherent structure of the data, but our assumptions about the geometric properties of latent variables may not apply in all real-world scenarios. We also suggest that the assumption of conditional independence between a data sample and its augmented version could be relaxed in future work, as it may not align with realistic situations. Our experimental results indicate that linear identifiability appears to hold even when some assumptions are violated. Section Summary. In this section, we present results demonstrating that our models effectively recover latent variables from both synthetic and real-world datasets, achieving high accuracy in identifying factors like object position and scale. We also find that representations learned through supervised classification outperform those based on instance indices, suggesting that even coarse classification tasks can yield identifiable latent representations, although our focus on controlled datasets highlights the need for further validation on larger, more complex datasets. Section: Implications for Deep Learning. In this section, we show that deep learning models trained with cross-entropy can effectively uncover the hidden variables, allowing for linear transformations. Our proof of identifiability, demonstrated with DIET, confirms that this holds true even in standard supervised learning tasks. We analyze the important role of cross-entropy in classification, which gives us a theoretical basis for understanding concepts like neural analogy making, transfer learning, and the linear decoding of features.